In this video, we will continue our discussion of L'Hopital's other indeterminate forms, those of the type 0 to the 0, infinity to the 0, 1 to the infinity. And recalling that the goal here is to algebraically rewrite, in terms of properties of exponentials and natural logs, to get back to those original indeterminate forms, 0 over 0 or infinity over infinity. So in this first example, it's a limit as x approaches 0 from the right of x plus 1 raised to the power cotangent. So the x plus 1 as x goes to 0 is going to 1. And as x goes to 0 from the right-hand side, cotangent x is going to positive infinity. So we have one of these indeterminate forms of the type 1 to infinity. So what we are going to do is rewrite using properties of exponentials and natural logs in much the same way that we would rewrite if we were to differentiate this function. So this becomes the limit as x approaches 0 from the right, and we'll have e raised to the natural log of that function, x plus 1 to the cotangent. But recall that if you have a power inside a natural log, it comes out front of the natural log. So now, if we think about x approaching 0 from the right, as we said, cotangent is going to infinity, and the natural log of x plus 1, since x plus 1 is going to 1, the natural log of 1 is 0. So it's of this type infinity to the 0, and we know a simple algebraic manipulation will get us to the desired point. So I'm going to move the limit inside the exponential, and I'm going to rewrite algebraically. So multiplying by cotangent would be equivalent to dividing by cotangent. And as a reminder, 1 over cotangent is equivalent to being tangent. So we can rewrite this algebraically as ln of x plus 1 divided by the reciprocal of cotangent, which is tangent. And now as x goes to 0 from the right, ln of x plus 1 still goes to 0, and tangent of x also goes to 0. So L'Hopital's rule, and remember every time we use it, we indicate with an LH, tells us that this limit is equivalent to the limit, where we take the derivative in the top, and we divide by the limit in the bottom. And now we're in the ideal situation. As x goes to 0, in the top, 1 over x plus 1 goes to 1, and secant squared of 0 is 1. So the value of this limit is e to the 1, which is simply e. So now one last example involving L'Hopital's rule. So let's evaluate the given limit. As x approaches 1 from the right, of x divided by x minus 1 over ln of x. So let's think about what's happening to each of these two functions individually. X over x minus 1 is a rational function which has a vertical asymptote at 1. And as you approach 1 from the right, the value of that function is approaching infinity. And I encourage you to graph that function in your graphing calculator just to verify. Similarly, if we think about 1 over ln of x, as we approach 1 from the right, ln of x is approaching 0 from the right. So 1 divided by a really small positive number is getting big. So also infinity. And this is actually our last type of indeterminate form. Infinity minus infinity is not something that has an associated meaning to it. You might immediately think, oh, it should be 0, but it turns out it could be any number. It could be infinity, minus infinity, or anything in between. All we can do is algebraically simplify and hopefully get to the point where we can apply L'Hopital's rule. So this is equal to, and the algebraic simplification we have would be just combining into a single fraction. The denominator would be x minus 1 times ln of x. So we need to multiply the first fraction by ln over ln, giving us x ln of x. And then we're subtracting away where we have multiplied the second fraction by x minus 1 divided by x minus 1. So now if we think as x goes to 1 from the right, the top is going to be going to 0, and the bottom is going to be going to 0. So we do have one of L'Hopital's indeterminate forms. So if we differentiate the top and the bottom, we get an equivalent limit. So the derivative in the top, we're going to start off differentiating x ln of x with the product rule. We'll take the derivative of the first, which is 1, times the second, plus the first times the derivative of the second. And then we're subtracting away the derivative of x. Similarly, we can differentiate the denominator also with the product rule. We take the derivative of the first, which is 1, multiplied by the second, plus the first, x minus 1, times the derivative of the second. And at this point, I'm going to go ahead and do a small amount of algebraic simplification. What I'm going to do is just multiply the top and the bottom of the fraction both by x. And the reason I'm doing this is just to make it look a smidge simpler. So we'll have the limit as x approaches 1 from the right, and in the bottom we'll have x ln of x plus x minus 1. And in the top, note that x times 1 over x is really 1. So we'll have x ln of x plus x minus x. So the plus x minus x terms actually cancel off. Now as x approaches 1 from the right, well, x ln of x is going to 0, as is x plus 1. So the top and the bottom are going to 0. So once again, we apply L'Hopital's rule. And we keep doing this until we get to a limit that we can evaluate. So recall that we've seen above, when we differentiate x ln of x, we ended up with ln of x plus 1. So when we differentiate the top, we're going to have ln of x plus 1. And in the bottom, note we are going to be differentiating x natural log of x, so that's also ln of x plus 1, plus the derivative of x minus 1, another 1. As we approach 1 from the right, ln of x is going to 0 in both the top and the bottom, but you have the leftover 1 in the top and 2 in the bottom. So the value of this limit is now 1/2. So note, when you see this new indeterminate form, infinity minus infinity, it's tempting to immediately say that that limit will be 0. But just like our other indeterminate forms, the value we get for the limit can actually be any number, which is why it's very important to go through this procedure using L'Hopital's rule. Combine into a single fraction, and then see if we can evaluate.